Okay, thank you very much, Professor Ida, for your kind introduction. And I'm so excited today to begin with this conference with delivering some flavor of flexible, stretchable electronic devices. And so this is the outline of my presentation. So after brief introduction, I will first talk about the stretchable electronics with an emphasis for smart wear application, and is going to talk about the ultrathin electronics and breathable nanomesh electronics, both of them emphasizing the sense application. And finally, I'm going to briefly touch the recent development of organic photovoltaic cell to supply electricity to ultrathin electronics. So let me begin showing the photo of electronic skin. You may not be familiar with the electronic skin. So what is the e-skin? That is truly stretchable, animal-like stretchable sensors that can detect the pressure and the temperature distribution simultaneously. So we try to realize the skin-like sensors by fully utilizing printable organic thin film transistors. So this video show you the manufacturing line to make the active metrics for large area sensors solely by using the printing process. So all the environment is kept in very controllable environment, and we can manufacture high definition organic thin film transistors only by using printing, which includes the inkjet, gravure, screen, and others. So ultra thin film is temporarily supported by the glass substrate and then handled by robot arm. And there is no human touch, and we can make the flexible devices with high yield. And this movie show you how our device works. And it doesn't look like flexible devices, but our devices could be manufactured on plastic foil, as mentioned. Thereby, the harsh motion, like the jumping, didn't cause any mechanical failure. But simultaneously, we can monitor the temperature and pressure distribution with high definition. And we can detect the temperature and pressure distribution simultaneously. And because of the mechanical flexibility, our thin film devices could be wrapped around the cylindrical bar like this, and then monitor the grip pressure with high spatial resolution. And immediately after the manufacturing the simply flexible electronic skin, so we instantly recognize how important to achieve the mechanical stretchability. So indeed, without stretchability, we cannot apply the e-skin onto a movable part like joint of arms, or it is impossible to put the e-skin onto the three-dimensionally curved surface like robot body. So to achieve the stretchability, our approach is very straightforward. So first, we put the two-dimensional array of rigid islands that are embedded into the rubber substrate, and then print the organic thin film transistors on rigid island. And finally, electrode could be connected by utilizing the elastic conductors. So in that way, when we stretch our integrated circuit, all the strains could be accommodated with changing the length of wires. So thereby, the strain could not be induced into the active layer like organic thin film transistors. So in that way, we can achieve the high stretchability over 145% without causing any mechanical failure. So here, the newly developed printable elastic conductors play a very important role. So you may see how the new material works. So we stretch our material printed on elastic substrate and connected to the light-emitting diode and battery. So you didn't see any change of light intensity from a LED. So that means the change of resistivity could be suppressed sufficiently low enough. And ink formulation is very straightforward. So silver flake could be mixed uh, together with the organic solvent and the surfactant among the rubbery fluorinated copolymer and mixed together and print onto the rubber substrate by screen printing and annealed at 140 degrees Celsius. Then we can achieve the high conductivity close to the 1000 Siemens per centimeter and high stretchability over 400%. So our device could be put onto the soft gripper, and on the fingertip, we can put the 8 by 8 flexible pressure sensing element. And you may see how our device works. And so those two balls look similar, but when we touch the soft ball, so contacted area is very large. But the blue ball is very rigid, thereby with application of the same force, the contacted area is very small. So in that way, we can distinguish the material stiffness by using this soft gripper. And also, such kind of similar technique may be transferred onto the rubber substrate, and that may be laminated on the surface of textile substrate. So in that way, we can make the textile substrate smart with introducing a lot of sensing functions. So such kind of approach is creating the new opportunity in the field of smart apparel. So here is the one example. The left figure shows the state-of-the-art electromyogram monitoring system widely used in sports field. So gel electrode could be attached on the skin, and external cable are connected between the recorder and attached gel electrode. So those configuration are widely used in sports field. However, this is not so convenient to monitoring the athlete motion. But if you look at the right figure, now all the electronic element, including electrodes, external wires, and recorders, are embedded into the sports wear. So it significantly simplified the installation of sensing element. So now, such kind of smart wear can detect the lot of different types of biosignal, including ECG, EMG, body temperature, and motion. So this movie show you smart wears to monitor the user's motion. In other words, so this is the motion capturing system based on the smart wears. So in this development, the 7 accelerometer could be embedded into the sports wears. And by utilizing the AI analysis, the user's motion can be precisely monitored. So those kind of motion capturing system usually requires the multiple camera setting, and then user needs to put the markers. So such kind of configuration is not necessary because our system is so easy simply by wearing the smart wear, and after 1 second calibration, that starts monitoring the user's motion. So because there is no need to put the multiple camera setting, Thereby, we can monitor the user's motion anywhere, anytime, even the outside the building, like during the sports or golf or running. And so this is quite benefit. And one of the tangible goal of such kind of smart wear is the sports application. And so she is the Miss Umehara, uh, a member of Japan's national team. And during the corona situation, so Miss Umehara has the difficulties to meet her coach in person. So during the corona situation, so we send our prototype to the Miss Umehara, and then she do some exercise with wearing our smart wears, and the coach sends his feedback online. And another application is remote rehabilitation. The person with spinal cord injury participated in rehabilitation session at home with wearing our prototype and communicated with his physical therapist remotely. So this kind of remote rehabilitation or remote medicine will be accelerating by the corona pandemic and getting more and more important. Another example is the smart glove. So unlike conventional glove type devices, stretchable electronics could be attached onto the very thin rubbery glove. So we make the highly stretchable conductors, and so that is the motion capturing system similar to the smart wear that I showed by the video. So in that way, we can monitor the user's motion very precisely with simply wearing the glove. And another recent development is the smart wear that can monitor the 3D ECG. The left figure shows the conventional Holter ECG. Again, that requires the match point electrode attachment that could be connected to the external cable to the recorders. So to put the electrode at the appropriate part of the body, the patient have to go to the hospital. But in this new development, all the electrode is embedded onto the smart T-shirts from the beginning. Thereby, we can send the smart T-shirts by regular mail. And as patient wear the smart wear and the electrode could be attached at the appropriate position, simply wearing this T-shirt. And after spending 24 hours monitoring, and then the prototype, this product T-shirts could be returned to the company. So in that way, we achieved the world first mail inspection of 3D ECG. So this is quite a good example to show the benefit of smart wears. So before this development, we always say, so what is the benefit of smart wear? So we say it's simple attachment, but we didn't explicitly recognize what does this mean. But now it is clear. When we try to put the multiple sensors at the appropriate part of the body, so it is so difficult and occasionally requires the assistance of nursing staff. But now we can put the sensing element at the appropriate part from the beginning, so without bothering the medical staff. So this is a really, really great benefit. So then I'm going to talk about the stretchable, from stretchable to conformal sensors. So this slide show you the epidermal electronics reported by Professor John Rogers. And Professor Rogers reduced the silicon tip down to a few micron, and which are temporarily supported by the plastic foil and directly attached on the human body, so which is called as epidermal electronics or electronic temporal tattoo. So this research triggered the extensive effort to introduce the electronic functions on the surface of a human skin. And thanks to tremendous effort of scientists and researchers, and now skin electronic devices could monitor a lot of different types of signals, which include the ECG, EMG, or EEG, or body temperature, skin modulus, hydration, or sweat analysis, including lactic acid and glucose. In our research group, focusing on the organic electronics, and we try to make the multiple electronic functions on the surface of ultrathin film with a thickness of few micron. So one of the good example is the ultrathin pulse oximeter, where red pellet, green pellet are integrated with organic photo detectors. This device could be attached on the surface of fingertip and obtains the very stable physical contact. So thanks to ultrathin film features, the sensor attachment doesn't cause any, pain of wearing. And because ultrathin film could establish the good physical contact, thereby it is quite strong against the, it is quite resilient against the motion artifact. And the previous device is single point detection, but we make the two-dimensional array and making the conformal imaging system with integrating organic photo detector with low temperature polysilicon. Our device could achieve the high spatial resolution over 500 dpi and high readout speed of 41 frames per second. When our device could be attached on the fingertip that can monitor the fingerprint like biometric information and start monitoring pulse wave like a biosignal. So in that way, same conformal imaging system is capable of imaging fingerprint or veins and measuring pulse waves. And then I'm going to talk about the nanomesh-based electronics. So because although ultrathin film electronics is so fascinating with integrating multiple semiconductor electronic functions, however, because of the lack of breathability, long-term attachment may cause the lot of skin problem like redness, itchiness, or skin inflammatory issues. So how we can solve that problem? So recently we have made the breathable nanomesh electronics. So it firmly adheres to the shape of the skin, and it is ultra thin and lightweight, and there is no sense of fit. So let me show you one video. So I'm afraid the sound didn't include it. So, so, so this is the ultra thin breathable nanomesh electrode. So, so the new sensor can be worn continuously without causing any inflammatory issues. And this is different development. Our skin in display can be freely deformed, and that can be attached on the human hand and exhibit a lot of vital signs monitored by the on-skin sensors. And acquired data could be monitored by the home doctor remotely. So let me show you the device fabrication. The nanomesh is made of polyvinyl alcohol, which is known as a water-soluble polymer by electrospinning method. And gold patterns are formed by vacuum evaporation through a shadow mask. And nanomesh electrodes are put on the surface of the skin and applied some water by spraying. The PVA is dissolved by water and washed away completely. Finally, breathable porous gold thin film could be remain on the surface of the skin. So left photo shows the nanomesh electrode. The shining part is the nanomesh gold electrode. So that looks like a continuous film. But if we magnify the image by SEM, so obviously that looks porous structure. And please look at the left down figure. So, and shining part is the gold, and non-shining part is the bare skin, and the dark spot are sweat pores. And if we look at the those sweat pore region near on gold layer, the same amount of sweat is penetrating both on gold region and non-gold region, and which showed the natural penetration of sweat and the natural vaporization of sweat could not be prevented by nanomesh. So such breathability is quite important to ensure the biocompatibility. Indeed, when the nanomesh conductors are attached on the surface, people's forearm continuously for a week, so none of the patients showed the doubtful inflammatory issues. But when the 1 micron thick polyethylene and 1 millimeter thick silicone are attached on the surface of forearm for a week, it exhibits the fairly high risk of inflammatory issues. So in that way, we prove the breathability is quite important to show the biocompatibility. And such devices could be attached on the people's near chest. And here we see the external module that is embedded on the E-Berry band, supplying electricity and data could be transferred smartphone by a readout wireless tip and start monitoring the electrocardiogram continuously without causing the any burden of sensor attachment. And also, we are developing the ultra-thin pressure sensors. So we are able to measure the contact pressure without affecting the skin sensation when the fingertip touched an object. Previous nanomesh sensors is simple gold single layer, but now we make the capacitor structure with sandwiching the nanomesh insulator with nanomesh gold electrode. Here you can see the nanomesh gold electrode and nanomesh insulator, and here is the bottom nanomesh gold electrode to form the capacitor structure. So when we applied the pressure, the spacing between two electrodes get closer, and then increasing the capacitance. So this is the sensing mechanism. So one of the highlights of our research is how scientifically prove the no effect of skin sensation by nanomesh attachment. Here is a way to show. So we lift up some object with putting some material on the surface of fingertip and try to monitor the minimum grip force with lifting up some object. And here is the result. So the black dashed line is the data of bare skin, and blue dashed line is obtained when the fingertip is covered by 2-micron thick ultra-thin film. So even though such thin film attachment may cause the slight increase of minimum grip force, however, the nanomesh attachment show the almost identical grip force with bare skin data. So in that way, we prove the non-effect of skin sensation by nanomesh is attached. And here we monitor the grip pressure with lifting up the very soft sponge with a weight of 0.16 gram and repeatedly pick up and release and pick up, release, and succeeded in measuring the contact pressure of such a soft and lightweight sponge ball by fingers. And finally, I'd like to quickly report the recent progress of organic photovoltaic cell. So our research group also developing the organic photovoltaic cell manufactured on ultra-thin film plastic foil to supply the electricity to the ultra-thin sensing element. But of course, we need to improve the environmental stability in addition to the improvement of quantum efficiency. So when our research began in 2012, the efficiency was 4%, but now it go beyond the 15%. And simultaneously, we try to improve the environmental stability and mechanical stability. With improving the mechanical durability or flexibility, then we try to make the waterproof organic photovoltaic cell. And finally, we achieve the thermally stable organic photovoltaic cell. And also we improve the conversion efficiency with optimizing the process condition or replacing the organic semiconductor with highly efficient material. And now we achieve the efficiency over 15%. And finally, I quickly show you the one of the application of organic ultra-thin film organic photovoltaic cell. So ultra-thin organic solar cell module is used to recharge the battery attached on the skin. So to obtain the sufficient electricity, we need the fairly large area. But when we put the large area organic photovoltaic cell on the backside of insect, that may cause the lot of motion motion interference. So to avoid that problem, we need the ultra-thin film and also a better sensor, a better attachment. And this graph show you, this view graph show you the normal ultra-thin film attachment, and this is the bent mode. In that way, ultra-thin film adheres to the insect body with interleaving structure to secure the bendability of the film. So with this combination of ultra-thin and novel thin film attachment on the backside of the insect, so now this video show you the benefit. Of course, when the insect will be flipped without film, it's easy to return to the original position. Original position. However, when thin film devices could be attached on the backside, that may prevent the natural motion. So we try to minimize such interference with reducing the thickness. So when the thickness is less than 5 micron or maybe 4 micron, so the insect could be returned to the normal position. But when that go beyond the 5 micron, the insect couldn't be returned. So in that way, we try to ensure the basic motion ability. So we examined the quite detailed analysis with changing the thickness. But again, if the thickness is less than 5 micron, with combination of interleaving attachment structure, and then we can ensure the fairly sufficiently good success rate of returning to the normal motion. And then this is the demo. So this is the before charging and after charging with organic solvent with light illumination. And then after charging and send the signals wirelessly, and we can change the direction of the insect motion. And then in that way, we demonstrated the successful system level demonstration of a self-charging system with ultra-thin organic photovoltaic cell to control the insect motion wirelessly. Okay, so before concluding my presentation, so I'd like to acknowledge my collaborator. So this photo is the our team of University of Tokyo who developed the skin electronics. And my team at RIKEN developed the ultra-thin organic photovoltaic cell. And the clinical evaluation was performed in collaboration with Keio University Hospital, and ultra-thin film electronics was developed in collaboration of Johannes Kepler University. And we also appreciate the contribution of our industry partner. So in summary and conclusion, today I report the recent progress of wearable devices or stretchable devices. So we are hoping that novel electronics that harmonize with human may create the new application opportunity in the field of healthcare, medical welfare, sports fitness, AR, VR, entertainment, and even more. So thank you very much for your kind attention.
Thank you very much, Takao. I think, as usual, this is a very interesting and remarkable presentation. And every time I hear you, we see something new and very, very astonishing results you present. So we appreciate your presentation. So if anyone have any questions, please put your questions in chat window, or we can also put it in the Q&A window. Alternatively, you can put questions on the Discord. If you want to speak in person, you can raise your hand, and maybe I can let you speak in front of all the audience. So, Takao, let me start with my questions. I have a lots of questions actually. But the first questions I want to ask you is something to do with the AI, machine learning, and maybe large language model, foundation models, and so on. Do you Okay, how much AI machine learning do you use in this kind of technologies? Or I'm sure there are going to be lots of implications of how they're going to be integrated to AI machine learning in the future, and smartphone and all the Apple, Samsung smartphone going to use these technologies in the future. So maybe you can just give us a bit comments about what you think the influence of this technology to AI in the near future.
Yes, thank you very much, Mia, for your wonderful first question. So currently, we use the AI only for the analysis of smart wears, the data with the data of several accelerometer. But I believe the combination of AI or deep learning with the wearable tech will create the quite bright future. So indeed, the multimodal sensing will be the key to examine to create the personalized medicine, because the health condition may vary depending on the individuals. So this is one of the important direction. And another important direction will be manufacturing of device, fabrication. So indeed, at some point, all of those device fabrication could be transferred to the fully automatic manufacturing, production line. So at that point, all the data could be collected to optimize the fabrication condition. In case of organic devices, we need the naive control of surface morphology, or so in such a case, the more advanced controllability of automatic fabrication is needed. So I think that's also the opportunities for the artificial intelligence. So.
Okay, thank you. Thank you very much. And I need to ask you one more very urgent question to you, because I'm sure lots of roboticists in this audience are so excited about your achievement, and they really want to use your sensors as soon as possible. But I'm sure there are lots of obstacles between you and us. And we want to know what do you think is the biggest obstacles use these sensors? I mean, you have a lot of different kind of sensors, but as you said, the manufacturing process, the production process, all of these things are still probably very difficult for other users of these technologies. Do you have any comments of what are the relatively low-hanging fruits for us to start using your sensors, or what are the more difficult, what are the fundamental challenges in this area of a production?
Well, this is also a great question. So I want to provide you a couple of remaining issues. So although the stretchable sensor works well and exhibits the quite good mechanical durability, however, we need the sensing system. Thereby, we have to integrate all the electronic element, including power supply and also readout module. Or so in such a case, the system needs the integration of stretchable soft element and well, maybe silicon-based rigid element or uh, rigid small rechargeable batteries. And then if those two soft and rigid element are integrated together, so and then try to make large stretchability. So the system couldn't be sufficiently durable. So we need to ensure the mechanical durability of the integrated system. This could be the real challenge in the future. And also, our device may exhibit the large stretchability. However, that's also cause the large change of performance. That may be okay for the sensing application, but we need the well, digital system. So that shouldn't be changed with introducing the large deformation. So that's also another big challenge. The last challenge is how we can supply the electricity, and this is not a trivial issues. So we need the good power supply that is collecting the power from ambient. Or we may establish the good wireless power transmission system. So that remains the quite open question.
Excellent. Thank you. Thank you very much, Takao. Carlos, do you have your hand is up? Do you want to ask questions and turn on your microphone?
Yes, thank you very much. Can you hear me?
Yes.
Yes.
Yep. Thank you very much for an interesting talk. This is all very new for me. I was wondering, it was not clear for me how easy would it be to use wearable skin not only for sensing but also for stimulation?
This is also a great question. So our research is somehow focusing on the sensing application, but we need the actuators or stimulation or actuators that in a combination of sensing element and the actuation system may create the bright future. But currently, we are working on the only sensing function, or more specifically, physical sensors. And for wearable tech, the detection of chemical information will be also a next important challenge. And also combination with stimulation or other actuation will be the next challenge. And then finally, we need the integrating everything like sensing, stimulation, or actuation, and the power supply, and also data analysis or transmission. So data transmission or power supply may be okay with rigid element, but when the everything could be attached on the skin, so and then we need the mechanical flexibility.
Okay, thank you very much, Takao. And there's another question over here. Most of the examples here shown on the surface of the body, but can you actually, are you thinking about this technology to be used in the inside our body?
Yes. So this is also quite exciting question. So in other words, the feasibility of implantable, devices. Our research group doesn't work on that topic so much, but development of implantable devices with stretchable or ultra-thin film uh, electronics is getting more and more popular. I believe there exists a lot of opportunities. But one of the issue is how we can get the industry involvement. So many of the large company is quite conservative and hesitate to work on the implantable devices because that is so risky. But I believe that also quite important research direction to go.
Excellent. Yeah, thank you. Cecilia, your hand is up. Do you want to turn on your microphone?
Yes, if we have time, very quick question. Thank you so much. I'm so fascinated by this technology. I'm not an expert, and I'm roboticist, so as Fumiya said, that's amazing for us. I mean, and we look forward to being able to use this kind of electronics now as soft robots. And another point that I have in my mind for soft robotics is biodegradability. So how far are we to have this kind of electronics that can really be integrated into a soft robot, into the formable bodies? How far are we to have a completely degradable kind of electronics?
Yes, so thank you very much asking the great question. And biodegradability is one of the important research topics. And Professor Jenan Bao, Stanford University, and Professor John Rogers, Northwestern University, are intensively working on the topics. And although our research group doesn't have any activities on the topics, so I think the biodegradability is very important. And also, if we try to make the large area electronics, recyclability or environmental impact should be carefully examined. So that also important topics from the viewpoint of material development with the emphasis of sustainability of society in the future.
Thank you so much.
Excellent, Takao. This was a fantastic opening of the AI conference, and now we're all excited and inspired from talk and discuss some crazy things in the next 2.5 days. So thank you very much once again. And if you have time to stay for another hour or two for the discussion, that'd be great. You can include you in the discussion later. But for now, we have a 15 minutes break. And then afterwards, we're going to have a panel discussion, short talks and panel discussions. So let's have a 15 minutes break, and we will see you all in this place again. Thank you very much, Takao. Good to see you in the very
Okay, thank you very much, everyone.
Thank you.